Yes.
Okay, so welcome everybody to the seminar today. So today is the first day of school, and also we are very happy to have two talks today. So we have two visitors. The first one is Kendo Fujita from Osaka University, and the second one will be Vanya Chesov from Edinburgh. So the first talk will be 1 hour, and then we will take a break for 30 minutes. And then after that, we're going to have second talk by Vanya. So Kento is going to talk about on the Calabi problems for fungal varieties. Okay, so please start.
Thank you so much for the introduction. This is a great pleasure for me to give a talk in this seminar. Actually, it's a second time for me to visit Taiwan. I like Taiwan very much. This is a survey talk, so please feel free to ask me. I start with very introductory. Firstly, the main topic is I would like to explain what is a evaluative criterion for K-stability of Fano varieties. The K-stability of Fano is motivated from the Calabi problem. It comes from differential geometry. So firstly, I would like to talk about what is the Calabi problem. And its algebraic interpretation and known to be K-stability. So I will explain what is the original definition of K-stability. And then its simplification named variative criterion. I want to explain. And finally, I will survey recent progresses. So it is a kind of preparation of Vanya's talk, next talk. For a smooth projective manifold, the following three classes are very important. Characterized as a positivity of the first Chern class, negative, zero, or positive. By Kodaira embedding theorem, those three numbers of conditions can be interpreted. Kx is canonical divisor is ample or zero or numerically equivalent to zero or minus k is ample. Called canonically polarized Calabial in weaker sense and Fano manifold. In this talk, the last one, Fano manifold, is the most important object. For example, if a complex dimension is equal to 1, then every complex smooth projective curve can be divided. One of them, genus is bigger than 1, genus is 1, genus is 0. But in higher dimension, if dimension is bigger than 1, then
Let me have
yeah, okay. Thank you. Okay, thank you. In higher dimensional case, in general, it does not belong to neither of them in general. But ideally, philosophically, all projective manifolds could be assumed to be decomposed in very rough sense into the above three very important classes. For example, a minimal model program, MMP in short, asserts that every projective manifolds can be decomposed into one of them in relative setting or allowing singularity. One of the typical singularity appearing in minimal model program is KLT. I will explain what is KLT, Kawamata log terminal in short. And I should remark that Fano, the last one, is very rare than the other two. So one of the important topic about Fano varieties are boundedness. And actually, boundedness of Fano is nowadays very understand in various sense. For example, smooth Fano manifolds are bounded by the Matsusaka's big theorem, it can be replaced that for any n dimension n, there exists large n depending only on small n, such that every n-dimensional smooth Fano manifold satisfies that its anti-canonical degree. This means anti-canonical degree. Degree is less than or equal to n. Actually, Kola and Miyaoka-Mori showed the boundedness by proving this boundedness of anti-canonical volume. But I should remark that Kola and Miyaoka-Mori's this effective bound is far from being optimal, I think. They gave the effective bound nth power of nth power of n like this. Anyway, and recently, Bilka showed that the family of n-dimensional KLT with additional assumption, epsilon KLT Fano varieties are bounded. So previously so-called BAB conjecture. Okay. And our main motivation is Calabi on Fano manifold is about the Calabi problem, complex differential problem. In 1950s, Calabi proposed the following question. For smooth projective variety X, give a condition admitting good metric, so-called Kähler-Einstein metric. Kähler-Einstein metric means Kähler declosed and satisfying Einstein equation. Rich omega is equal to some constant times the power of the original omega. I called the problem to be the Calabi problem, but I heard that Kähler already pointed out this question, so it should be better to add the name of Kähler. But in this talk, we call it the Calabi problem. Okay. In order to consider this question, existence of Kähler-Einstein metric implies the very strict condition of the condition of X, because rich omega represents the first Chern class. So if X admits Kähler-Einstein metric, then X must be one of the three classes I explained before. If lambda is negative, then first Chern class is negative, 0, positive. So in order to consider this Calabi problem, we may assume one of them in advance. And for each cases, the problem is Kx is ample case or Calabi case, Kähler-Einstein metric always exists. So the Calabi problem is affirmative without any condition due to Orban and Yau independently, and this is famous Yau's theorem. On the other hand, the only remaining problem is Fano case. For Fano manifold, Kähler-Einstein metric may not exist in general. Actually, there are many Fano manifolds does not admit Kähler-Einstein metric. So from now on, we concentrate on the Calabi problem for Fano manifolds. And let us say basic properties on the Calabi problem for Fano manifolds. The first one is very well known. If X is a projective space, then we know that a projective space admits Fubini study metric. And the Fubini study metric is Kähler-Einstein by explicit computation. So for Pn and in the product of Pn projective space, the Calabi problem is of course affirmative, but there is an obstruction. I will explain obstructions. It means a necessary condition. if Kähler-Einstein metric exists, Matsushima showed that the automorphism group of X must be a reductive algebraic group. It means the identity component is reductive algebraic group in usual sense. So, from this Matsushima's obstruction, del Pezzo surface of this and this does not admit Kähler-Einstein metric because automorphism of group of this and this are not reductive. And the second obstruction found by Futaki is I do not explain the Futaki's obstruction seriously, but for every Fanon manifold X, there is a Lie-algebra homomorphism from the space of homomorphic vector field to C, defined only from the information of X, such that Kähler-Einstein metric exists, implies that this F is identically equal to 0. And actually, those two numbers of obstructions are very strong. In fact, Tian shows that if dimension is equal to 2, two-dimensional Fanon. In other words, if X is del Pezzo surface is two-dimensional Fanon, then existence of Kähler-Einstein metric on del Pezzo surface, if and only if X is neither isomorphic to the guy blow up 1 nor 2 point. So if dimension is equal to 2, that is del Pezzo surface case, Matsushima obstruction, or I do not explain, but Futaki's obstruction is enough to check the Calabi problem. But those two obstructions are not enough, unfortunately. For example, Matsushima's obstruction, Futaki's obstruction tells nothing if automorphism group is finite. If finite is reductive. If finite, then the tangent space at identity is this space. This vector space is 0. So if X automorphism group is finite, then those obstruction results say nothing, but there is a Fanon threefold such that the X does not admit Kähler-Einstein metric. So, but due to Tian, but Tian's construction is to degenerate Mukai-Uemura threefold. So Tian's construction asserts that it seems to be important to consider the one-parameter subgroup of auto X that Futaki considered, but also the degeneration of X is important in order to consider the Calabi problem. Nowadays, the information is called as test configuration. And then notion of K-stability appear. Thanks to those and also many other differential geometers' contribution, it turns out that the condition, the Calabi problem, strongly relates with the some stability condition of the variety itself due to Yau, Tian, and Donaldson. So now we can say what is K-stability, mainly due to Yau, Tian, and Donaldson. So taking 3 numbers of people, Yau, Tian, and Donaldson, so previously called YTD conjecture, that Fanon manifold admits Kähler-Einstein metric if and only if X is some algebraic stability condition called K polystability. And in this talk, 3 numbers of stability condition reappear: K stable, K polystable, and K semi-stable. Strictly speaking, there are many other, and more precisely, more stronger K stability condition named uniform K-stability is also important. But nowadays, it turns out that uniform K-stability is strongest one, and K-stability is equivalent. So in this talk, it's a survey talk, so we do not distinguish with strongest uniform K-stable and K-stability. So I will be very loose at the difference between uniform K-stability and K-stability. Okay. And the K-stability is purely algebraic condition. So, original Calabi problem is for Fanon manifold, but we can very easily, without any harm, to generalize the stability condition for very singular Fanon varieties, not only smooth Fanon manifold, but also singular Fanon varieties. And but how much singular we should treat? But here is a very remarkable result due to Odaka, such that singular Fanon is, if singular Fanon is K semi-stable, then X is Kawamata log terminal, KLT singularity. So I think it's a first result such that encounter with K-stability and minimal model program. Actually, after his result, it turns out that K-stability is very friend with minimal model program. Okay, so thanks to Odaka's result, from now on, we consider the Calabi K-stable, polystable K-stability problem for only KLT Fanon variety. Okay, and not recent. About 9 years ago, YTD conjecture is solved by Chen Donaldson Soon and Tian independently. So I said that conjecture, but it's theorem. Yeah. And as I said before, K-stability is for any test configuration, the information of the degeneration of X, it's certain GIT weight, so-called Donaldson and Futaki, DF, Donaldson-Futaki invariant, is somewhat positive, very roughly speaking. I will explain what is the K-stability rigorously. Okay. I said I typed test configurations. So now I will explain what is K-stability. In order to show what is K-stability, we should firstly introduce what is test configuration, the information of degeneration. Okay. From now on, X is KLT Fanon variety. Let X be an n-dimensional Fanon variety. A test configuration, curly X and curly L of X consists of the following data. There are various notions of test configuration. So, but I choose one of them. Yeah. Strictly speaking, I should say normal and compactified test configuration. But yeah, we lose it. The test configuration consists of information of degeneration. So it's a family. Curly X is a normal projective variety with a surjection onto P1. So family over P1. And L is relative polarization, an ample Q-line band. Together with C and is equivariant, C star equivariant. GM is the C star multiplicative group. The action compatible with the action to P1 multiplicative action, where T is the non-homogeneous coordinate of P1. And the GM equivariant isomorphism. Curly X outside zero fiber is isomorphic to X times P1 minus 0. And the polarization is minus K. So this is the definition of test configuration. So the figure of test configuration, curly X is the following. The total space of the degeneration. And outside zero fibers are, all of them are X. But on zero fiber might be degenerate. For this is a definition of test configuration. And what is the Donaldson-Taki invariant? Is determined by this intersection number. Strictly speaking, this is not the original definition. Original definition is due to Tian and Donaldson, and later Xiaowei Wang and Odaka independently rephrase in the word of this intersection number formula. So it's not a definition but a theorem. But in this talk, here is the definition. Now we are ready to say what is K stability. Firstly, X is X is K semi-stable if for any test configuration, its Donaldson-Taki invariant is non-negative. And K polystability and K stability are similar. K polystable if K semi-stable and equality case holds only if degeneration is X itself. And stability is similar. Semi-stable and DF0 holds only if the totally family is trivial. So GM equivalently, the test configuration is isomorphic to X times D1 together with anti-canonical polarization. Okay. Those three numbers are definitions of K semi-stable, polystable, and stable. And it looks very similar, K stability and K polystability. In fact, K stability is nothing but K polystability and automorphism group is finite. Okay, so far, is there any question or comment? No, okay. Firstly, I saw this original definition. It seems to be that it's tough. Because in order to test K stability, we must consider infinite number of test configuration, the information of n plus one dimensional object, and compute some invariant. So given Fano manifold, it's very tough originally, whether it's K stable or not. So I wanted to simplify the definition. So I will introduce one of the simplification nowadays called the evaluative criteria. I wrote that let F be a prime divisor over X. Yeah. That is, there is a resolution of singularity sigma X tilde to X such that F is a prime divisor on X tilde. Yeah. The variative criterion is in order to prepare what is the variative criterion, let us consider any prime divisor F over X. Prime divisor over X means this. Yeah. Okay. For every prime divisor F over X, we introduce two numbers of invariant. The first one is very common for birational geometer, known to be log discrepancy. That is, large AX of F is defined to be 1 plus the coefficient of relative canonical divisor. It's very, very common because, for example, the definition of KLT is nothing but for every prime divisor F over X, log discrepancy is bigger than 0. So the standard, highly standard. But the second one is less standard. But all the mathematical notion appearing in the definition is very common for higher dimensional algebraic geometry. Sx of S. Some people call the value expected vanishing order, defined to be 1 over anti-canonical degree times the integration of the volume of this R-Carty divisor. Let us recall what is volume. Volume is the growth of the dimension of the global section. So M is said to be big if volume is strictly positive. And let us analyze what's this function behave. Firstly, if t grow up, then the divisor is less effective. So H0 is decreasing. So this is a decreasing function. And it is known to be the continuous function with respect to the value t. So, and if t is equal to 0, it's nothing but a degree. And if t is very, very big, then this divisor tends to be non-pseudo effective. That is, volume is identically equal to 0. So this integration is integration between 0 to bounded area and a continuous function. So not so strange integration, but it still seems awful to consider this value. If we know, we have a knowledge of, you have a knowledge of Okounkov body, then this value is very simple. So computation of Sx of F. Let us explain the value expected vanishing order Sxf in terms of Okounkov body. As before, let F be a prime divisor over X. And let us take model X tilde such that F can be realized as a prime divisor on X tilde. I forgot to mention that the values log discrepancy and Sx of F does not depend on the choice of model. Yeah. Okay. And okay, now let us explain in terms of Okounkov body. Okounkov body can be determined from the information of so-called admissible flag, that is a sequence of closed subvarieties of codimension 1, 2, 3, n. So Fn is a point. Such that some smoothness condition, each subvarieties of codimension i's are smooth at the last point. And let us assume that the first stage, codimension 1 flag is taken to be F. That's the most important. And from this admissible flag, we can it is somewhat well known that we can construct some convex compact set, so-called Okounkov body of minus k, more precisely Pulbach of minus k, with respect to the admissible flag. I do not explain the precise definition of Okounkov body, but the Okounkov body reflects many positivity property of this line bundle, in this case, minus k. For example, this is this convex set is the Okounkov body. For example, if the volume of minus k, anti-canonical volume of minus k is nothing but the nth power times the volume of this Okounkov body. Moreover, volume of minus k vanishing along f at least x times is the n times volume of the set of Okounkov body such that the first coordinate is bigger than x. So this red area, the volume is nothing but this volume. So let us take to be Qx to be this blue restricted volume. Okay, now what is Sx of f? Recall that Sx of f is the divided by the. It's the definition. And as I explained that, this volume is red area. So integration from x to infinity of qi, restricted volume. And denominator is this from 0 to infinity. And if we change integration firstly from y to x, then this integration can be replaced this guy. So Sx of f is nothing but the first coordinate of the barycenter of the Okounkov body. So it's very, very simple value. Yeah. Okay. And later, I will recall this Okounkov body representation later. Okay. I introduce log discrepancy and this Sx. A variative criterion is formulated as follows. Let X be a KLT Fano variety. X is K semi-stable if and only if A is bigger than or equal to S for every prime divisor of X. And stability is replaced as follows. Strict inequality. Equality is changed as strict inequality. And here is a very highly non-trivial result due to Liu-Shu-Zhuang that AX is uniformly bigger than or equal to SX. Actually, this last condition is we should call uniform K stability. Liu-Shu-Zhuang says that uniform K stability is equivalent to K stability. But in this talk, we lose the terminology. Yeah. Okay.
Need to check for all f that over x. But is it possible that we just check some specific devices?
Yes. Actually, this is a very important question. Yeah. Actually, for K definition of KLT, we only need to one log resolution, and that's all. But for originally variative criterion, we need to consider every prime divisor of X. So many people want to decrease the number of F. For example, today I do not prepare it, but I showed that we only check F with PLT blow up, PLT type. And if I will explain later that if reductive algebraic group G acts, then we only need to check all F with G equivalent, G invariant. But in any case, a priori, we must consider infinite numbers of F. So problem cannot be highly simplified in general. At the moment, yes. You're right. Okay, so from this, those numbers of theorem criterion, it's very natural to consider the ratio of A and S. So A and S. So it's a direct corollary of variative criterion that KLT Fano is K-semi-stable, respectively. K-stable if and only if delta X, so-called delta invariant, or stability threshold is bigger than or equal to 1, respectively bigger than 1. Where delta is the infimum running through all F prime divisor over X, such that the ratio A over S. I should comment that the original definition of delta invariant introduced by myself and Odaka was not this form, using some more quantum-wise definition. But later, Brammer and Johnson says that our original definition is nothing but this. Okay. So, the problem is how to estimate this value. So, the Calabi problem can be reduced to this problem. How to compute this? And yes. It's a nice, great condition. Yeah, question. Yeah. Actually, I introduced the prime divisor F to be product type, and K polystable if and only if X of F is bigger than or equal to SFX, and equality case holds only if F is product type. But the notation is not so good. That turns out to be. Yeah, we can rephrase along the context, but it turns out that to kill the torus action is more convenient. That is, in place of considering delta X, but delta torus invariant X. Torus means a maximal maximal torus of the automorphism group of X. So I mean, it's better to consider K-stability killing automorphism group. So, yes. It turns out that K polystable is equivalent to people called reduced uniform K-stability. So, modifying this invariant is more important. So sorry. I just want to mention that we can also have which is just like general, more general. Sorry, I can't understand the question. Maybe I didn't ask question. Oh, please discuss later. Okay. And this criterion looks not, some people think that it's not strong, but this theorem indeed has lots of application. And I will introduce one of the application. Actually, I talked this application 9 years ago in Taiwan. An application is the following. For any k semi-stable n-dimensional KLT fan variety, if X is k semi-stable, then its anti-canonical volume is less than or equal to this value. So the projective space is 1. Moreover, equality holds if and only if X is isomorphic to Pn. So I said in the beginning that Korami Okomori shows that n-dimensional smooth funnel is the family is bounded, but the upper bound of anti-canonical volume is far from being optimal. But if we add k semi-stable, then allowing singularity is also okay. But anyway, anti-canonical volume is optimally bounded. Proof is very, very, very simple. Let us take any smooth point and let us blow up at the point and let F be the exceptional divisor. It's a Hartson exercise that log discrepancy is dimension n. Yeah. And in order to estimate S invariant of F, S invariant is integration of this value. And this value is bigger than or equal to anti-canonical volume minus nth power of t, because recall that volume is the growth of the dimension of global section. So if small k grows, then this the growth of this global section. But from this very simple exact sequence, the growth of this is bigger than or equal to growth of this. So my degree minus growth of this. Yeah. So we get to the conclusion. N is the log discrepancy. Log discrepancy is XF is bigger than or equal to S invariant. But S invariant is estimated from, thanks to this value, volume is bigger than or equal to this. And volume is a non-negative value. So we are only interested in a positive area. And this integration is that. Together with inequalities, we get the assertion. And equality case can be done by Chou-Miyaga Shepard-Baron type criterion. Okay. And I should remark that this kind of treatment, volume estimate using this kind of exact sequence is highly generalized for the theory of normalized volumes. The theory of normalized volume is of independent interest. Actually, Qi Li introduced this notion of normalized volume, and Yu-Chen Liu and Harold Bloom, etc., generalized a lot. Okay. And I will explain the recent progresses. It's a kind of one of the answers of Junkai Sensei's question that if X is a KLT fan variety and if a reductive group G acts on X, in order to show K polystability, ideally we must consider infinite number of prime divisor over X. But if A is strictly bigger than S for all G invariant prime divisor, then K polystable. So yeah, it's very just add the G, but very strong, and the proof is highly non-trivial due to Zick and Zhuang. So if the deductive subalgebraic G is very big, then the number of F is very restricted. So let us introduce local delta invariant. Take any closed subvariety Z. Let stability threshold along Z is the ratio of A over S infimum taken to be F is prime divisor over X such that the center of F contains Z. By Zick-Zhuang's theorem, in order to show the K polystability of X, it is enough to show that local delta invariant is bigger than 1 for every G invariant closed subvariety Z. Because for every G invariant prime divisor F over X, its center means the image of F, must be G invariant subvariety. So if this guy is bigger than 1, the ratio, of course, bigger than 1, then applying Zick-Zhuang's theorem, K polystability, we can show the K polystability. So the one of the trivial application is if X is a rational homogeneous space, then there is no G invariant auto invariant closed proper subvariety. So trivially K polystable. But the problem remaining is how to estimate local local stability threshold. Yeah, it's still a difficult problem, but recently, Aban Zhuang's method, Hamid Aban and Zick-Zhuang Zhuang have a very strong theory in order to estimate the local stability threshold from below. Actually, their theory is very huge, but in order to explain, it's very tough. So we restrict the situation. And I remember that I already explained this Aban Zhuang's theory in 2 years ago via online in Taiwan. But anyway, let us recall Okounkov body. To make simplify, I only consider on X. Previously, I explained on X tilde, but let us consider on X. Take any admissible flag, codimension 1, 2, 3, n of subvarieties with each yi is smooth at the point yn, admissible flag. As I explained, let us consider the Okounkov body of minus kx with respect to the flag yi. And let us take the barycenter to be b1 bn. As I explained that the first coordinate of the Okounkov body is nothing but the S invariant of the first one, that is y1. And surprisingly, Aban Zhuang shows that for any codimension J, the local delta invariant of Yj is right-hand side inequality is trivial. This guy is smaller than equal to ax of y1, that is 1. Log discrepancy of y1 is 1, and sx of y1 is b1. So this inequality is by checking the ratio of y1, it's trivial. Avalanche 1 shows that this left-hand side inequality. Actually, they show that the minimum of 1 over B1, 1 over Bj can be estimated. So, in order to consider Calabi problem, it's enough to estimate the local stability threshold. And if algebraic group are large, we only need to check local local stability threshold for G invariant Z. And to estimate the invariant, if we can take a suitable flag such that the Okounkov body, the barycenter of the Okounkov body with respect to suitable flag is near to the origin, that is, the minimum is very large, then X is K polystable. So the game reduced to be finding a good flag. Actually, for many cases, we can apply this technique. Actually, Fano threefold, three-dimensional case, we have a very satisfactory answer. Let us recall that about the three-dimensional Fano varieties. It has been known that by Iskowski and Mori-Mukai that there are exactly 105 families of three-dimensional Fano manifolds. In our joint research with Clarina Araujo, Ana Maria Castvarez, Ivan Chertov, and Sophie Karagiros, and Jesus Martin Garcia, and Kostya Shramov, and Henrik Sand, Nibeta Vitisvana-san, that we consider the Calabi problem of Fano threefold. We determine the K stability for each family, but each family has, of course, in general, positive dimensional base, but so it's very tough. But we consider it for general member, for each member, is whether K stable or not, K polystable or not, K semi-stable or not. That question is actually well defined, and here is a theorem that exactly 78 general members is K polystable, and the others are not. And similar for stable and semi-stable. And actually, the main tool is to estimate the stability threshold with respect to finding good flags and so on. Yeah. And this is a recent progress related to my research. But I should mention that there are many other progresses. One of the big progresses are about moduli theory, projectivity of the K moduli space. Yeah. I will explain very briefly about recent very big progress, Chen-Yan Xu, etc. due to fix n dimension and v anti-canonical volume. Let us consider the K moduli stack KSS is S inside S is a scheme over spec C with a big FPPF site, and for scheme over S corresponds to this groupoid whose set of objects are family over S of n-dimensional K semi-stable KLT Fano with volume V and dimension n, and satisfying some mild condition, so-called Collatz condition. Let us consider this pseudo functor K moduli stack. And here is a very big theorem due to many people. So I cannot say who did. And final setting due to Liu Shuzhuang that the shield functor is actually an algebraic stack of finite type. So Artin stack. And the algebraic stack admits the good moduli space in the sense of alpha. That is, there is a morphism from this stack, algebraic stack, to algebraic space denoted by MKPS, such that the morphism is cohomologically affine, and the morphism push forward of structure sheaf of left hand side is the structure sheaf of right hand side. Actually, good means functorially very good. For example, the set of C-valued point of KPS is one-to-one corresponding to the set of isomorphism classes of K polystable n-dimensional anticanonical volume V Fano varieties. That's why I denoted KPS. And finally settled by them that the algebraic space admits the ample line bundle, so-called CM line bundle. In particular, the space is a projective scheme. So general setup is, general theory is nowadays completely understood. So the next step after this is, what's the structure of this? Yeah. About this. It's natural to analyze the structure of the component, irreducible or connected component, especially the component such that containing smooth guy. In fact, if Del Pezzo case n is equal to 2 case, then the space is very well understood thanks to Odaka Spotty soon. So our current research is to consider n is equal to 3. How about n is equal to 3? So considering a scheme structure and which Fano threefold should be degenerate as a K polystable. One of the theorem due to Banyan and Tiago is we determine the connected component M number 3.9 and number 4.2. Those guys are generically parameterized using Fano threefold number 3.9 and 4.2. Actually, we analyze the scheme structure of the and the. Those guys can be written as a GIT quotient. And probably on the next talk, Vanya explain another compactification. So I'm looking forward to his talk. And here is a summary that the 9 authors result, as I explained, is started from AIM conference and nowadays finished and published in London Mathematical Society as a book. The book contains the topic as I explained, history, variative criterion, case stability of general members, but also many topics. For example, I did not explain what is alpha invariant. It's classically very important. And it's still very important even now. And how to compute the stability threshold of a Del Pezzo surface. And our main result is about general member. But if automorphism group is infinite, then we have a complete answer for the K-poly stability of Fano threefold. So the most important thing I want to say is, if you are interested in the problem, it is grateful to buy our book. Okay, well, that's all. Thank you so much.
Any questions?
Exactly one general Fano threefold, which is K semi-stable and which is not K polystable. What is this Fano threefold?
Blow up around V5 around 9.
Along a line.
V5
V5. Okay. Yeah.
On V5 means linear section plus 1 to 5 3 times.
Three times.
On V5, space of that line is quite a parameter. There are two types of lines. One is good normal bundle of the line is 4 plus 1. The other one, is the bundle line. Is the normal bundle 4 minus 1 plus 4. If blow up around bundle line, then the function is unstable. But general, good blow up from good line, then the function is semi-stable, but not polystable. Actually, in order how to show strictly semi-stable is to construct a polystable degeneration.
So in this case, the K, so the good moduli space is empty in this case, or a good moduli space associated to
1 point.
Yes, K polystable degeneration. A good modular space, there are no smooth points. Smooth point.
Mhm.
All are stuck.
I see. So just one pointer.
Yes.
Thank you.
So in the middle, you have a filtration F1, IR, Fn, and so on, and with a very center B1, and Bn. So I'm asking, do we have any kind of optimal construction for the filtration? And do you have any analytic aspect of the construction?
By experience, generally we have no systematic algorithm to find suitable problem, but we experimentally know how to find it.
Well, for example, is it possible to apply, I would say, Hughes multiplicative ideal shift, that kind of analysis, L2 analysis? Is it possible to do that in that direction?
Not direction. It is a very interesting question.
Any other questions? Okay.